Welcome to EEG Tutor. I'm your personal EEG tutor, Dr. J. Kays McKay. A bit about me, my background was that I completed a neurophysiology EEG fellowship at the Mayo Clinic in Florida. I developed a lot of passion for EEG, and I was also involved in some international education regarding EEG. This program is designed to teach you to become an intermediate EEG reader. The program starts with short lectures covering the fundamentals of EEG and gradually builds you up until you're reading seizures and status epilepticus. You got to trust the process though, guys. Take it one lecture at a time in sequence, and before long, you'll be reading EEG with both competence and confidence. Without any further ado, let's get to it. During Lecture 1, I will cover biophysics underlying EEG. Provided here is an outline of the topics I will focus on. A key principle I want you to remember is that you should understand, not just memorize EEG patterns. While some pattern recognition is necessary in EEG, the more you rely on the understanding of the underlying principles of how an EEG is generated by the brain, the less likely you are to fall into traps such as misidentification of artifact as an epileptiform abnormality. EEG is a complex topic, but we can start with the fact that the brain is composed of cells called neurons, which together generate an electric field. This concept was discovered and taken advantage of by Hans Berger, who first invented the electroencephalography machine in 1924. While I won't dwell too much on EEG history, it is worth storing away this frequently referenced name as a part of your EEG knowledge. He is a somewhat controversial figure since the nature of his contribution to the Nazi Party during World War II is debated. Though some claim he was forced into a position helping the Nazi Party against his will, other sources have claimed he was more or less a willing Nazi collaborator. In the end, he died of suicide by hanging himself on June 1st, 1941. However, he left a legacy that largely revolutionized neurologic diagnostic techniques with a technology of EEG that is still used 100 years later. The EEG records electrical fields of the brain with electrodes, and this activity is expressed as continuous waveforms. Over time, we've added more electrodes and built on the knowledge of different EEG patterns. I'll expound upon this as this lecture progresses. An important concept to understand from physics before we go any further are dipole moments. A dipole moment is simply the separation of charge with a positive and a negative end, with an actual net charge of zero. So if this white orb represents a zero charge, and then you separate out the positive and the negative ends, the net charge is still zero, but now you have basically something that can generate a field, an electrical field, between the positive and negative ends of this. You'll see this concept come back around quite a bit during this lecture, so I want to introduce it right off the bat. As mentioned, neurons are the fundamental contributor to the EEG electric field. There is some help from other brain cells called glial cells, which only contribute a modest amount. The soma of neurons is where all the organelles and all the machinery is located that makes the cell work overall. Axons transmit signals and dendrites receive them. Axons are vastly outnumbered by dendrites on pretty much any given neuron. Neurons have resting membrane potentials at minus 70 microvolts, meaning the inside is more negatively charged than the outside. This is maintained by the cell membrane, structurally not allowing the transfer of negative charged large particles inside the cell, like proteins, and also ion channels or passageways. When an axon meets a dendrite to communicate, chemicals called neurotransmitters are released in the area between them called a neuron synapse. This is a diagram I made here where you see these little vesicles, these circles carrying blue neurotransmitter, which is released into the neuron to neuron synapse. Here is a 3D model version of this same concept where you have this axon having synapses with the dendrites on this other partner neuron. Excitatory postsynaptic potentials occur when a significant number of receptors in the synapse bind excitatory neurotransmitter, such as glutamate. This leads to depolarization or less polarization of the membrane as positive sodium ions rush in and make the inside of the cell less negative compared to the outside. Inhibitory postsynaptic potentials are often triggered by the neurotransmitter GABA, and they work the opposite way by leading to the influx of negatively charged chloride ions or by moving potassium out of the cell. Pyramid neurons are a specific type of neuron that are most active in creating the electrical fields measured by EEG. Their cell bodies are in cortical layer 5. They have long branching apical dendrites which interact with axons overhead, and these synapses add up and create the electrical field of the brain, which is predominantly measured by EEG. Excitatory potentials create neuronal dipoles. It depends where you have the excitatory potential, which type of dipole is created. Here we see a pyramidal neuron with an apical dendrite, and there's an excitatory potential affecting the distal end of this synapse. So, excitatory potentials at the apical dendrite cause a sink as positive charges of sodium and other ions rush into the dendrite, leaving a more negative charge outside of the apical dendrite synapse. This leads to a separation of charge, with the negative region outside of the apical dendrite and a more positive region relatively in the soma. The negative charge region in this case is the active sink, and the positive region is the passive source. Excitation of the dendrite near the soma, however, leads to a different result. The negative region being more in the location of the soma as positive ions rush in from the synapse in this region, creating what is known as a passive source closer to the apical dendrite. Inhibitory potentials are the opposite. Inhibitory potentials cause negative ions to enter the axon, and this leads to a more positive region outside of the axon in that region. In this case, this is a more proximal version of the synapse along the axon, so there's a positive region along the proximal part of the axon in what is called a passive sink near the apical region. Of the approximately 100 billion neurons in the brain, each may have thousands of synapses. So even though the electrical field of each one is small, they add up greatly. Electrical potential energy is another important concept to introduce. You can think of it as being similar to the energy stored when you stretch out a rubber band, storing energy, and then release one end of the rubber band, releasing that energy back. The stored energy is potential energy. Electrical potential energy is the amount of energy needed to move a positive charge against an electrical field. A positive charge will naturally move towards a negative charge. If you hold the positive charge from moving to the negative charge, this is electric potential energy. Voltage is the difference in electric potential energy between 2 points. This basically describes how much electricity is driven to move between the 2 points. Another way to conceptualize this is to consider how much the electrical potential energy of a positively charged particle would theoretically differ if we move the charged particle from one point to the other one. You may wonder how electrodes work and how they actually do this. The EEG measures electric potential differences between two electrodes over time, which is reported as fluctuating voltage over time. With that in mind, you may wonder how an EEG actually records local electric potentials with electrodes. Oscillating electrical potentials cause current flow, which is picked up by electrodes and transmitted through current flow in the wires. Electrode paste leads to an electrical double layer. This is an important concept. The electrical double layer allows for increased capacitance, which leads to an increased flow of current. This does introduce some problems, as the electrolyte paste and the electrode do have some independent chemical reactions which are picked up and form something called a half cell potential, which is like half of a battery. You have to cancel this out by comparing one electrode to another, because presumably this would be similar to all electrodes involved in the recording. I'll go through this process called electrode differential amplification later in this lecture. In general, electrodes are composed of silver chloride electrodes because this is a stable material that is resistant to polarization. EEG electrodes record the electric potential in the nearby region of the scalp, and this again has to be amplified, and you have to cancel out some noise with differential amplification, which I'll describe in a second. Amplifiers are very key, though, to allow us to actually get these signals to be big enough to where we can see them and interpret them. If the contact between electrodes and electrolyte paste is inadequate, you may have an issue with impedance. Impedance is another important EEG biophysics concept. Impedance is summarized as how much opposition to AC current flow there is between two electrodes. If the electrode-electrolyte scalp interface is not correct at one electrode, the impedance will rise, leading to a high impedance or high opposition of current electrode, which creates artifact. I'll expound upon this concept further in the artifact lecture. Now we'll reach the final concept we're going to cover during this lecture. The overall electrical field or signal of the brain is very low compared to the environment. There's a lot of electrical noise in a hospital environment with ICU machines, computers, whatever, causing electrical fields. There's a process called differential amplification where we compare one electrode to another. This allows for the background noise to be largely filtered out, as the background noise of both electrodes is about the same. This is what we talked about before with the half cell potentials that are generated from the chemical reaction of electrolyte paste and electrodes. You cancel these out essentially as you compare one electrode to another, and this would be about the same in each. One way to think of it is this. Here's a schematic. You have a head, there are two electrodes, E1, E2, which is called electrode 1, electrode 2. If you do E2 minus E1, then you essentially are having E2 plus the background minus E1 plus the background, and this big background or this gray area is canceled out, and you're left with what is equivalent to E2 minus E1. All right, it's time for some questions. Don't get too nervous, but let's just test a couple basic principles that you should have down after this lecture. If not, it's okay. You can always watch it again and review. First question, who invented the EEG? Was it Tom Pleck, Hans Berger, Werner Heisenberg, or Max Planck? Think about it. If you answered Hans Berger, then you are correct. Hans Berger, as mentioned before, is the controversial father of EEG, who developed initially a 2-channel EEG and actually discovered what's called the alpha rhythm. We'll talk about that more in the next couple lectures. Question 2. Where are the electrical potentials measured by EEG primarily generated? Are they generated by the neuron cell bodies, the axons, or neuron to neuron synapses? If you answered synapses, you'd be right. Final and third question. What the heck is voltage? Is it the difference in electrical potentials between 2 points, force times mass, or the amount of energy to move a positive charge counter to an electrical field? If you answered the difference in electrical potentials between 2 points, you'd be correct. Force times mass is going to be more like gravity. And then the amount of energy to move a positive charge counter to an electrical field was the electrical potential. These are the references I largely referred to when creating this lecture. All of these sources are excellent references to keep in your own library. I wasn't paid by them to say that. I have no affiliation with any of them, though I did learn from Dr. Tatum. The 3D neuron models earlier in the lecture are from Microsoft PowerPoint stock 3D models. And then the drawings throughout the lecture were actually my own. You might have suspected that based on how they look, but thanks for bearing with me. Well, guys, we'll end here. Congratulations for making it through the biophysics of EEG. These are some heavy concepts, but you made it. Take some time off to rest your brain if you need to, and then join me next time for the technical aspects of EEG. I'm your personal EEG trainer, Dr. Jake McKay.